Hi, welcome to lesson 22. Today we're going to start talking about the dual linear program, and we're going to approach it from a particular direction that is algorithmic in nature and actually harkens back to stuff you learned in Calculus 3 when you did something called Lagrange multipliers. Not sure if you remember that, but if you do, it might help you in understanding the next lesson. Anyway, the complication that I found that students have when we start talking about the dual LP is now we have multiple forms of linear programs, and it's important to keep them all straight. And part of the way we keep them clear which LP is which is we understand why we're doing it. And with that is the understanding they are all very different. So I'm just going to talk about what we mean before I get into this lesson. We have the general linear program. This includes any optimization with a linear objective, which you could be either maximizing or minimizing, and you have linear constraints. And I should note, for technical reasons, there are finitely many linear constraints. We don't allow infinitely many linear constraints. You might ask, well, when does that come up? And the answer to that, one simple answer to that is, if you think about it, if you can describe a circle with infinitely many linear constraints. That's clearly not linear, or at least I hope we all agree that that's intuitively not linear. And that's one of the many reasons why we don't allow infinitely many linear constraints. Anyway, that's a general LP. This is the broadest class. It includes every kind of linear program that we will ever talk about, of course. Okay, from there, we talked about canonical form. And remember here, it's a linear objective, so the objective is really the same. But it's equality constrained only. And it's over non-negative variables. So the only kinds of equality constraints allowed are what are called simple non-negative constraints. They're constraints just on a single variable, and that variable is greater or equal to 0. Otherwise, if there's a constraint, it has to be an equality constraint. And we do canonical form. Remember, this is just because this is the form expected by our version of the simplex method. And I should also note that every general LP can be transformed into a canonical form. So when we talk about canonical form, it is a restrictive form in the sense of what it looks like, but every general form LP can be turned into a canonical form. Then this week, what you've been thinking about is the phase 1 LP. And this is starting from canonical form. You introduce artificial variables and solve an LP that determines the feasibility of the original canonical form problem. The confusion, and I've heard it from some of you even this week, and it's an understandable one, is between artificial variables and the slack variables that we sometimes add to canonical form, or the surplus variables. Do not confuse these. Artificial variables are not slack, or surplus. If you have questions about any of these forms, please let me know, and I'm happy to address them. The thing I really, really, really want you to keep in mind is these are all different things, and that we're going to add another linear program in this lecture and the next one called the dual. And that's going to be yet another linear program. So you can see we now have, on top of the many definitions, we actually also now have different forms of linear programs themselves. I will note that along with the basic solution definition difficulty, this is also a very difficult topic that I'm introducing today. Our students have found it quite difficult. So I fully expect many of you to have questions, and that's fine and reasonable. The assessment 4, we're finishing assessment 3 this week. Assessment 4 is actually going to be given out on Monday, and it's going to be on this topic. Okay, so let's motivate what we're going to do now. We find that we're going to want upper and lower bounds on the optimal value of a linear program. Why do we want that? Well, a lot of times you won't, when you're doing an algorithm, you want to know an estimate of what's going to happen. And so this gives us that. So algorithms that consider linear programs as sort of a sub-problem rely on the upper and lower bounds. And we want to know how we do this. Duality is a powerful topic. It's, I think, the most powerful tool in the theoretical box of linear programming that came out of the theory of it all. And it's used in many different areas. And it's actually used in a modeling sense. And we'll get to that in the weeks after this as well. Anyway, let's motivate it with an example. We're given the following linear program. Please don't be scared off when we say z star equals the result of this. Just think of z star is equal to the value at optimality. Okay. So whatever that optimal value is, z star is another name for it. Okay. So it's in this case, the maximum, the objective value when it's at its max, subject to the constraints. So given a feasible solution, how does this value compare to z star? Well, you would expect if any solution that's feasible, it has to have, by the definition of optimality and the max, z star has to be greater or equal to the value of any feasible solution. So let's just see what a possible feasible solution might be. An easy one would be x1 equal to x2 equal to x3 equaling 0. And of course, its objective value is just 2 times 0 plus 3 times 0 plus 4 times 0, which of course is equal to 0. And that, of course, has to be less than or equal to z star. Maybe we can be a little bit more clever than that. And let's see, what else would work? What if we said x1 equal to 0, and maybe x2 equal to, let's say 4, and x3 equal to 0. The value here, oh, it's just 4 times 3, it's 12. So it's better than our 0, but it's still less than or equal to z star. In general, of course, we can say any x1, x2, x3 satisfying 1, 2, and 3, the constraints, has 2x1 plus 3x2 plus 4x3 less than or equal to z star. Right? That's by the definition of the optimal objective value. Any feasible solution is a lower bound on the optimal value for a maximum linear program. And of course, we want the highest lower bound possible. In some sense, that's another way of phrasing what it means to solve these, right? The optimal solution is, by its definition, the highest lowest bound possible. And I don't want you to get confused that we're now starting to talk about bounds. Okay, we're talking about bounds, and we're going to see why that is. But it's going to be helpful to talk about in this framework. Okay, so lower bounds on a max problem are just finding a feasible solution and computing the objective value. And of course, note that parenthetically, finding upper bounds on a min problem is the same. You find a feasible solution, and compute the objective value. Okay, so just keep in mind that when we talk about this, the context of whether we're minimizing or maximizing is very important. More difficult is finding upper bounds for a max problem. How do we do that? And I'll note again the parallel thing. The parallel difficult thing is finding lower bounds for a minimization problem. We want the lowest upper bound possible. And how do we do that? So we can think of it this way. We can use the constraints. The fact that we have constraints actually can help us. So for example, we note that any feasible solution has to satisfy constraint 1. And so what do? Well, what if we just multiplied any feasible solution, evaluating the left-hand side of constraint 1, and we multiply it by 3 halves on both sides. So let's see, constraint 1, what was constraint 1? Constraint 1 was given here. It was 3x1 plus 2x2 plus 5x3 is less than or equal to 18. So this is 3x1 plus 2x2 plus 5x3 is less than or equal to 18. And I know that if I multiply this side by 3 halves and this side by 3 halves, any feasible solution still has to satisfy that. And what I get back is I get something that's 9 over 2 times x1 plus 3x2 plus 15 over 2x3 is less than or equal to 27. Now you might be wondering, what is the point of all this? Why did I do this? Compare this to the objective. Well, what was the objective? Let's look back. Let's just look at that objective. It's 2x1 plus 3x2 plus 4x3. Well, I know that x1, x2, and x3 are non-negative, right? So that means that 2x1, which is less than or equal to 9 over 2x1, right? Because x1 is non-negative, so it's just 9 halves of a non-negative thing is greater or equal to 2 of that same non-negative thing. 3, of course, is equal to 3, so 3x2 is equal to 3x2. And 15 halves times a non-negative thing, and 15 halves times x3 is greater or equal to 4x3. So I can write out that 2x1 plus 3x2 plus 4x3 must be less than or equal to 9 halves x1 plus 3x2 plus 15 halves x3, which is less than or equal to 27. So that should make you go, give you the O emoji, because this is now an upper bound on the optimal value, because any feasible solution has to satisfy this inequality, including the optimal solution. So the optimal solution has a value of at most 27. But we can actually do better than that. Okay, how do we do better than that? Well, this we got just by taking some we took 3 halves times the first constraint. Let's use both constraints. Okay, so let's take 1 half times the 3x1 plus 2x2 plus 5x3, and that's less than or equal to 18. We'll take 1 half times that. And we'll add it to constraint 2. Wait, what was constraint 2? Constraint 2 was 5x1 plus 4x2 plus 3x3 is less than or equal to 16. So we'll just add it to that. So it's 5, 4, and 3. Okay. So now we have 5x1 plus 4x2 plus 3x3 less than or equal to 16. And I'll just add both sides, and I know that I maintain my inequality. So this is 25 on the right-hand side, and this is going to be 3 halves. It'll be 13 halves x1 plus 5x2 plus 11 over 2x3. Okay, again, when I compare this to the objective, I see that each of these coefficients in front of the x1, x2, and x3 is greater than the corresponding 2x1, right? So 13 halves is less than or equal to, I'm sorry, is greater or equal to 2. Five is greater or equal to 3, and 11 halves is greater or equal to 4. And because, again, there are non-negativity bounds, I know for any feasible solution that this 2x1 plus 3x2 plus 4x3 is less than or equal to the 13 halves x1 plus the 5x2 plus 11 halves x3, which is, we just showed it's less than or equal to 25 because of the combination of the constraints. Okay, I'm going to stop there, and I'm going to ask you to address example 2. Take time and just play with this. I'm going to put in online